Hello and welcome to the 8th lecture. From this lecture onwards, we shall start a new topic which is about IC voltage regulator, integrated circuits voltage regulator. In the last 7 lectures, we studied 2 power electronic devices, that is SCR, silicon control rectifier, and TRIAC. In this lecture, we look at the syllabus and the book used for this topic of IC voltage regulator, and we shall begin the topic of internal circuit arrangement, and under that we will complete the subtopic of Zener reference. So these topics are part of your syllabus for IC voltage regulator, internal circuit arrangement, Zener reference, regulation protection, error amplifier, series pass transistor, 3-terminal positive voltage regulators, 3-terminal negative voltage regulators, 3 and 4 terminals adjustable voltage regulators, 4-terminal positive voltage regulators, 4-terminal negative voltage regulators, dual non-tracking voltage regulators, and dual tracking voltage regulators. The book that we shall use is Modern Power Electronics by P.C. Sen, and Sultan Chand is the publisher. So let's begin the topic of IC voltage regulator. See, voltage regulator, as the name itself suggests, regulates the voltage such that you get a constant voltage. Now, before this integrated circuit technology was developed, a voltage regulator was made using discrete components. So you will take a diode, you will take a capacitor, you will take a transistor, you will take some resistors, you will connect them and make a voltage regulator. But in this part of our syllabus, we will be studying about IC voltage regulator versus the discrete voltage regulators. So a voltage regulator has become almost mandatory for power supply of electronic equipments and various control circuits, because all the equipments and control circuit would require a specific voltage, a specific current. So they would not run directly on the 230 volts or 220 volts or 240 volts which is supplied by our main. From the plug in our house and in the offices, we get 230 volts AC. But most of the equipment will not be able to run with that. So we will need a voltage regulator which gives us the required voltage that the device requires. Now the performance of this voltage regulator, performance and reliability would depend upon the characteristic and overall reliability of the regulator. So the performance and reliability of our equipment and the control circuits would depend upon the characteristics and overall reliability of the regulator. Now when we go to buy a regulator, there are some parameters that we keep in mind. We keep in mind its size. We do not want a huge and bulky regulator. We keep in mind its weight. We don't want a heavy regulator. And of course the price. We don't want a very costly regulator. Now, due to these concerns, IC technology has crept into this area, because when you use an IC technology, its size reduces, its weight reduces, and its cost reduces. All because it uses a monolithic structure, a monolithic technology. So we have a wide variety of monolithic linear voltage regulators available in the market. Now what are the advantages of using an IC voltage regulator versus the discrete one? So this IC voltage regulator have eliminated the tedious and repetitive task of designing power supplies. So when we did not have IC regulators, we had to design a power supply, use discrete components and shoulder that circuit. But now you just need to get a ready-made IC and you are done. Now the characteristics of this IC regulator are much better. What are the characteristics? Operating temperature range, that is IC voltage regulator can operate within a wider temperature range than the discrete voltage regulator. Variation in output voltage with temperature. Usually when the temperature changes, it has its effect on the output voltage. So this variation of the output voltage with temperature has been minimized in an IC voltage regulator as compared to the regulator made using discrete components. Now an IC voltage regulator has built-in protections which improves its reliability and which makes it virtually immune to failure modes, which we get many a times when we use discrete voltage regulators. So these protection circuits would be circuits which would protect us from overload, short circuit, temperature variations, etc. So it has reduced cost, and along with that it has high reliability and flexibility, due to which IC voltage regulators are indispensable in almost every practical applications. Any electronic device you take would have an IC voltage regulator inbuilt in it. We say that IC voltage regulators are extensions of the discrete component type regulators because initially the discrete component regulators were made, and then all those discrete components are managed inside a monolithic IC. So in that way we can call them as an extension of the discrete component type regulators. Now these IC regulators can be of fixed voltage, that means it will give 5 volt or 10 volt or 15 volt, a fixed voltage, or it could be adjustable series regulator. That means you could decide or you could change the output voltage by changing some resistors. So you could have 5.5, 7.5, 8.5. Within a range you can adjust your output voltage. And these regulators would give either positive or negative output voltages. So you have 5 volt, minus 5 volt, 10 volt, minus 10 volt. So these all things you could get using this variable or adjustable series voltage regulators. Now generally the IC voltage regulators are low power devices. So power is current into voltage. So the output voltage could range from 2.5 to 30 volts, and the current capabilities could be from few milliamperes to 10 amperes. But you could connect some external components and you could extend its power capacity to up to 100 kilovolts, and you could increase its output current to the order of tens of amperes. This is by connecting external components to the IC voltage regulators. Now IC regulators are of two types, general type or precision type. In the general type, you cannot adjust the output voltage precisely, but their power capacity can be extended with external components, and these are simple and they have 3 terminals, one terminal for input, one terminal for output, and one will be the common ground terminal. Then you have precision type IC regulators. You can have their output voltage precisely set to any value over the range of 5 to 50 volts. And the input voltage that you give to these precision type voltage regulators could be also within a bigger range. The range of input voltage could also be larger. They have more than 3 terminals, and the designer has a choice to control the regulator according to the requirement. Control in a sense of setting the precision voltage, the current. Now, so what is there inside this IC voltage regulator? So let us look at the internal circuit arrangement. This is a block level arrangement. If you see it physically, you will see there are a lot of transistors in it. But we will not be looking at that type of circuit, but a block diagram will be studying. So this is a block diagram of an voltage IC regulator. Vs is the input voltage that you give, Vo is the output voltage that you get, and this is the common ground between the input and the output. So this is the protection circuit, we will be studying it in detail. Constant current supply, startup circuit, voltage reference, error amplifier, and R1 and R2 form the feedback circuit in which a part of the output is given as feedback to the input. So this feedback is compared with the reference voltage, and depending on the difference between the reference voltage and the feedback, the error amplifier generates an output, and this output is given to the series pass transistor. So depending on this output, this transistor would either increase or decrease the output voltage. So suppose our output voltage is more than the required value, then the feedback will be more, due to which the output of the error amplifier will become less, due to which the base input of the series transistor will become less, so it will allow less voltage and thus the output gets decreased. Now suppose if the output has become lower than the required value, in that case the feedback will also be less. The difference between the reference voltage and the feedback will be a greater value, due to which more input will be given to the base of the transistor, due to which it will allow a higher value of voltage to pass through this, and thus the output voltage will increase. So in this way the output voltage is maintained at a constant value. If it increases due to this error amplifier, the value is decreased. If it decreases below the required value due to this error amplifier and this transistor, the value is increased. So in this thing, the value of this reference voltage is very important. It should remain constant. It should not change with respect to temperature, because the feedback is compared with this reference voltage and the output is adjusted according to the difference between this reference voltage and feedback. So it is very important that the reference voltage remains constant. If the reference voltage changes, the output will also change accordingly. So this reference voltage has to be stable. It should have low temperature drift. That means there should be very less effect of temperature on its value and free from noise. There are two types of reference voltages. One is called the Zener reference, another is called the band gap reference, which are widely used. We shall study only the Zener reference as part of our syllabus. Zener reference. As the name itself suggests, that it is obtained from a Zener diode, which is fed by a constant current source and is temperature compensated by a string of diodes. Now let us look at this diagram. This symbol is a symbol of a constant current source. You have the Zener diode here. This is the resistor R, which limits the current through the Zener diode, or which sets the current which will pass through the Zener diode. Now, base emitter of this transistor Q2 is a diode, as a Zener diode is, and the temperature coefficient of this transistor is set by the constant current I. Now, when the value of this I increases, the temperature coefficient of VBE goes down. So this value is so chosen that this temperature coefficient cancels the positive temperature coefficient of this Zener diode. So due to a change in temperature, there will be a positive temperature coefficient here, and the temperature coefficient here will be of the same value but of the opposite polarity. So the effect of a change in temperature will cancel out from each other. So your V reference voltage, which is equal to V is inner voltage plus VBE remains constant because both of them have opposite temperature coefficients, and this is adjusted by this constant current source. Thank you.